So we'll record this session so that people who aren't here right now can look at it later. So if I'm going too fast, or if you guys want to ask a question, definitely do so. You can do so in chat. You can do so just like raise your hand and ask a question. There's also these buttons that say go slower or go faster, and so you can use those, and me and the TAs will try to pay attention to how you guys are all doing. So let me take you to this slide. So this is our review for exam 3. Something just made a weird noise. And so basically the homework assignment for the rest of the kinetics unit is due Friday, and that's problems from 7C, 7D, 7E, and then the back of the book, and then also quiz 10. So I've heard that Learning Suite is being really buggy right now. It's really swamped with users and information. And so if Learning Suite is not up, we're going to move deadlines if needed. So don't worry about it if come Friday you can't upload your information. We'll make allowances for that. The other thing that's true is that lecture 1 on nuclear decay, the quiz associated with that lecture is due on Friday. But that doesn't make sense because nobody is trying to look at nuclear decay right now. You guys are just studying for exam 3. So we'll move that quiz to Monday. So a question was asked about keys, and will the keys of the homework be posted after the due date so you can study for the test? I think that's a great idea. Let's make sure that that happens. So I believe that Jack and Kimberly and Esteban already have the keys to the homework. We have to make up a key for the quiz, but that can be done pretty readily, and we'll make sure that that's up. Okay, so then let's talk about the exam. So with Learning Suite being a little weird, if Learning Suite is at all slow, which we project it to kind of be slow by Monday, what we're going to do is we're going to email you out the exam, and the exam will be a combination of multiple choice and open answer, but the open answer will be all done in a Word doc template. So you'll answer by highlighting different problems or answering what's going on in that Word doc, so that all we get back from you is the emailed Word doc with when you started the exam and when you ended the exam. And that should help with the Learning Suite situation. So we would email this to you Monday at 8 a.m. and then it needs to be sent back to us Tuesday at midnight. And again, I'll send you more emails out about that before that happens on Monday. We'll finalize everything by Friday, and you'll see an email about that then. Okay, so any questions about this front material situation before we get started on the review? Just gonna wait. I also don't have my headset today because I took it home because I was gonna work from home, but that didn't happen. So hopefully tomorrow I will work from home. Okay, so let's get started. Let's start with redox. So redox is the short term that we use to talk about reduction oxidation reactions. And let me just pull everything up. In the redox reactions, kind of some of your main points is that your redox reaction is 2 separate half reactions. So one has to be undergoing oxidation, and one has to be undergoing reduction, where oxidation is the electrons are lost. We've moved from a neutral or a low oxidation state to a higher oxidation state. Those electrons being lost create cations. So that's electrons lost is oxidation, and then electrons gained is reduction. And so when you think about these, this is that initial thing that we talked about where there's those mnemonic devices. So Leo the lion says grr, loss of electrons is oxidation, gain of electrons is reduction, and then oil rig is the other way to kind of remember these things. So the other thing that we talked about is identifying oxidizing and reducing agents. So the oxidizing agent is the species most likely to be reduced, and the reducing agent is the species most likely to be oxidized. And so these are kind of the terminology that we use for redox reactions. The half reactions are the specific oxidation and reduction reactions, and then the loss and gain of electrons. So if you're looking at a list of chemical equations, you can determine if it's redox if you have an exchange of electrons. And so looking at oxidation states, you have to have something that is oxidized and something that is reduced in order for it to be a redox reaction, because there can be no exchange of electrons unless you see something oxidized and something reduced. Okay, so then we talked a bit about balancing redox reactions, and there was the half reaction method where you break it up into half reactions and balance all of the elements except of hydrogen and oxygen, balance oxygen using H2O, balance hydrogen using H+, balance the charge using electrons, cancel species and combine everything. And then if you're in basic solution, all you do is react both sides of the equation with hydroxide to react away the excess H+ that we have here to form water, and then hydroxide, and then you kind of cancel out your waters. So that's the long way of balancing redox reactions. I don't know if I didn't put in the shortcut way, but I know that Kimberly is going to cover it in her review session. So it looks like a when is good link was sent out to ask students about the best time, but nothing's been confirmed. So so I think that a review will be scheduled for that, and they'll go through that kind of faster way for balancing reactions. But and both ways will get you to the same answer if you remember in class. I mean, it seems like ages ago, right? But if you remember, the only thing that feels bad is that at the end of the day, it feels like magic with that other way, but it does work out, and it's a little bit less steppy. So that's the redox reaction and balancing redox equations. So then with the redox couples, then when you break them up, you're going to have an oxidation half reaction and a reduction half reaction, which is what we talked about. So here's your oxidation half reaction loses in electrons, reduction half reaction gains in electrons. And so here we've got zinc metal, and it is oxidized to zinc 2+, and then we balance out that 2+ charge with 2 electrons. And then in the reduction, you have a silver plus cation plus 2 electrons, and that gives you 2 reduced silver metal atoms. And so you can kind of determine which one's oxidation and reduction based on where the electrons are. So oxidation is going to kind of produce electrons, and reduction is going to take electrons. So then we refer to these two half reactions as a couple. And so these couples are always written as the reduction. So the reason why this is important is because in a few slides, we're going to talk about standard reduction potentials. And in those standard reduction potentials, everything is written as the reduction couple. And so you would just use it in your calculations to know what is being oxidized and reduced. So anyway, so formally couples are written as reductions. So zinc 2+ to zinc is your is this half reaction, and then the silver couple is the plus over the reduced. So that's just how we write them. I'm seeing some people unmute. So if you unmute, raise your hand before you unmute so that I know that you want to stop me. Okay. Oops, that. Okay. So then galvanic cells are basically if you take half reactions and you put them in separate containers, and then you allow for a pathway for electrons to move as well as for the salt to balance the charge. Then you can get current associated with the difference in the redox couples or in the reduction potentials. And so a galvanic cell allows you to do that, and then that's all going to be measured in voltages. So then we talked a little bit about the notation for cells. So if you remember, you have your anode electrode, and your electrode is often an inert material. So we talked about it being platinum, we talked about it being carbon, we talked about it being the actual metal itself. And so your anode electrode is some kind of metal that can go into solutions. So in this case, this is your zinc and this is your copper. And these are both the electrodes because they are metal and they are conductive. But if our oxidation side was hydrogen or some kind of gas, then we would need some other electrode that was a solid instead of a gas to be able to react over there. To be able to, sorry, not to react, to be able to transfer the electrons through the galvanic cell. Okay, so the way that we write this is anode electrolyte, double bar, cathode electrode, bar, cathode electrode, cathode electrolyte, cathode electrode. So this double bar means salt bridge, and this bar means a phase change. So you don't always see the bar. If these are the same phase, then you see a comma. If you're missing your salt bridge, it's not there. And so then when you draw these things, you end up with kind of like a container and a container with the anode and the cathode. The anode is where oxidation occurs. So remember, if you group your vowels and your consonants, you'll get them right. So anode and oxidation both start with a vowel. Cathode and reduction both start with a consonant. And then you've got your salt bridge that allows ion migration. So where you're forming cations, you need anions to migrate. Oh, sorry. And then where you're forming, where you're removing cations to the reduced metal, you need cations to migrate. Okay, so then that's kind of like the notation for cells and drawing cells. So we talked a bit about that. I don't know what this says over here. Yeah, so the ion exchange is necessary so that it doesn't come to a halt, essentially. So that salt bridge, if you didn't have it there, you would build up so many cations, and you would remove so many cations that electrons could no longer flow. And so the salt bridge allows the electrons to continue to move. Esteban, can you see, what do you see? Do you just see the slides, or do you see all the things I have up on the slides?
Just the slides.
Okay, perfect. I see a chat window and everybody in the class, and so I was just making sure you didn't see all of that. Okay, so I think we have a couple more slides on redox. So here's an example of, here's an example of the annotation for this cell. So you've got your zinc electrode, your zinc electrolyte, your salt bridge, your cathode electrolyte, and then your cathode electrode. Whoops. Okay, so then, make sure I have everything up. Okay, so then we talked about that cell, and then how do you calculate the energy, useful energy associated with that cell. So the Gibbs free energy reaction, delta G standard, is equal to negative N being the moles of electrons that you have moving, times Faraday constant times the standard potential, or E naught. And that's for 1 bar of pressure, and then mostly somewhat, 1 molar solutions, which is somewhat dilute. It's not too concentrated. So in this reaction, the number of moles N is coming from your balanced chemical equation. So if you look down here, if I have permanganate and dichromate, and those are in a redox reaction, I would have to balance these 2 reactions together to find how many electrons actually were balanced at the end of the two half reactions added together. So right now you're like, oh, do I have to make a choice between 5 electrons or 6 electrons? And both of those answers are wrong, because you have to add the 2 sides together and come up with a balanced chemical equation with a balanced number of electrons on both sides in order to find your N molar amount of electrons that are being used for the standard potentials. The other thing we talked about with standard potentials is that the standard potential doesn't change with concentration. It changes with number of electrons being exchanged. And so this N value is what matters here, how many electrons are going through. So then this E, this standard potential, is the difference of the standard potentials between your cathode and your anode. And so if you always take your cathode, or whatever's being reduced, minus your anode, then you don't have to worry about any sign conventions. The other thing you can do, because everything is in all of the couples formally are written as reduction potentials. And so the other thing that you can do, I don't want to say this because I don't want to confuse anybody, but you can take your cathode plus your negative of the reduction potential of your anode, right? So that flips that sign here. But basically, if you just take your cathode minus your anode, then you should be fine in terms of finding your standard potentials. So this number, E naught, is what you plug into here. If you were to plug in your standard potential of your cathode or your standard potential of your anode, then what you are implicitly saying is that you're saying that the other half of your reaction is hydrogen, because everything in the standard potential table is normalized to hydrogen. So you can't just plug in one or the other. You always have to have a cathode and an anode, because redox is oxidation and reduction together. So so plugging in just one, you're basically making an assumption that the hydrogen is the other one. So then when predicting spontaneous reactions, you always need your delta G to be equal to less than 0. And if that's true, then your standard potential needs to be greater than 0. So spontaneous redox reactions will have standard potentials, the difference in standard potentials, so the EMF, electromotive force, EMF, is going to be greater than 0 for it to be predicted to be spontaneous. If the E naught of two things subtracted together is negative, that means that it's not going to spontaneously go. So if you think about this permanganate and dichromate answer, I can take 1.51 minus 1.33, and that would be a positive value, or I can take 1.33 minus 1.51, and that's going to be a negative value. And so you can predict that the permanganate is going to be the cathode, it's what's going to be reduced, and the dichromate is going to be what's oxidized, because that gives you the positive EMF when you take the difference of those standard potentials. Whereas the dichromate is not going to be reduced, and the permanganate is not going to be oxidized when I couple those two reactions together, because then I get a negative standard potential. So that's kind of what's happening there. So I think this page is where I finally have my list of all of my standard potentials. And so again, we've got this standard reduction potentials in water at 25 degrees Celsius. And so here's all of my reduction half reactions. So tables are formally tabulated as the reduction potentials. And again, if something is the anode and not the cathode, you're just going to flip that chemical equation to go in the opposite direction. And so these are all, so basically if you have a positive E reduction, that means that these will all reduce in the presence of a hydrogen anode, essentially. And then these will not spontaneously reduce in the presence of that anode. So the more positive the potential is, it means that it's got a greater electron pulling power of the half reaction, and it's going to be a stronger oxidizing agent. So the more positive it is, it's going to be an oxidizing agent, which means it's more likely to be reduced. So again, if you think about something like fluorine, fluorine with a negative charge, fluoride, has that octet, basically. It has the electron configuration of, I want to say argon, I don't know what it, neon probably. And so that is kind of a way to help you think, okay, like this is the most oxidizing agent, this is the strongest species that will be reduced up at the positive standard potentials for reduction up here. So then other points that we made in redox is that then aside from being able to get your Gibbs free energy from the moles of electrons that are being exchanged, you can also get the equilibrium constant. So the equilibrium constant, you have a relationship between delta G and K, and therefore you can replace delta G with the part of K, and then the equilibrium constant is going to be equal to either in this form or this form, the exponent of the number of moles being exchanged times Faraday's constant times this electromotive force difference in standard potentials divided by the gas constant and that temperature. So this gives you equilibrium constants. And so one of the applications we had in your slides was that you can find the solubility of like the solubility constants using a galvanic cell if you wanted to using this. Okay, and then the last thing we talked about was the Nernst equation, which says what if I don't want to be at equilibrium and I want to be away from equilibrium? So Q again is your reaction quotient. So that's how far are you away from equilibrium and in which direction. And so that gives you, if I have concentrations that are different than those found at equilibrium, then I can drive a cell one way or the other based on that concentration. And then when the concentrations change to reach equilibrium, that usually means your cell is dead. So the Nernst equation is actually really valuable and applicable to alkaline batteries, lithium batteries, all sorts of batteries that we use, where you make a cell that has different concentrations of the electrolyte, and then those concentrations eventually come to equilibrium, and then your battery is dead. So if you wondered why your batteries are dead, that's why. And then the next question people will ask me if we weren't studying for an exam is like, well, what happens when you have rechargeable batteries? And the rechargeable batteries, you're just running the cell in the opposite way, which is known as electrolysis, to get your concentrations back to what they were before they changed. I see a question. Will these equations be on the test? So there's a true-false portion again, where some of the equations are on there but might have like a different negative value to see if you know which ones are negative or positive or whatever. So I think most of the equations are on the exam. I'm gonna have, is Jack here? Jack, are you here? Jack, can you go take a look at exam 3 real quick and just kind of let me know privately if there are any equations that look like they're missing, and then I'll let you guys know in like 10 minutes. Can you do that, Jack, real quick? Where are you? Yes, maybe?
Yes, I can do that.
Okay, thanks, Jack. So Jack's gonna check up on that real fast. I think most of them are on there, but we'll let you know in a minute. We'll get back to you. Okay, so we'll go over, so do we need to know assumptions for the equations? Yes. What is the format of the test? I talked about that at the very beginning, but we can talk about it again at the end. So we're gonna keep going. I did put in a slide about electrolysis. Okay, so then for electrolysis, which is what I was talking about in terms of rechargeable batteries, is that you're just using a current to force the reaction to happen. So you're just driving it in the opposite direction. And so why this is helpful is let's say the major form of aluminum is the oxidized form, but this is actually true. So the major form of aluminum is kind of aluminum oxide, but aluminum oxide is very difficult to use and shape because it's brittle, and so you need to form the aluminum metal. And so what you do is that you use a current to force aluminum oxide to the aluminum metal by using electricity to make that reduction happen. And so electrons are basically being pumped in as electricity, and then oxidation still takes place in the anode, reduction still takes place in the cathode, but now the electrons are kind of like going upstream. So it's going in a non-spontaneous direction because you are providing energy to drive that reaction forward. And so that's just an electrolytic cell. That process is known as electrolysis. Whoops, sorry, right here. So this is the electrolysis situation. Okay, I think that's it for redox. And we're all gonna take a breath real quick. Let me see where I'm at. Okay, we're going to take a breath. I'm going to keep going just so we can make it through kinetics. Kinetics will go faster because we have just seen it, and then we'll take questions. So kinetics. So again, kinetics. The first thing we started with is difference between average rates and instantaneous rates. An average rate is just kind of going to give you really vague estimate of what's happening with the rate of your reaction, where an instantaneous rate is going to be tangential to the curves, and those instantaneous rates will be used to find rate constants. And so then your unique average rate is based on stoichiometry, and so that allows you to then relate how much of HI is being consumed versus how much of H2 is being produced. Because if I have a rate of the reaction, that's not going to be the same for HI and H2 in this reaction, because I have 2 moles of HI being consumed for every 1 mole of H2 being made. And so being able to multiply by that stoichiometric coefficient gives you that unique average rate. And then there was a lot of slides about determining orders and rate law from experimental data. And in that, what we had is that the rate was 0 order if the rate was equal to the rate constant and totally didn't change with any increases or decreases in concentration of the reagents. If you increase or decrease the concentrations of the reagents for a first order reaction, that means that your rate will change proportionally to the change in your concentration. So if I double my concentration, my rate doubles, that means that it's first order. And then if you have a second order, it means that if you double your concentration of a reagent and then it's, hold on, Jack, I can't do that. I can't do that. Jack, can you ask Kimberly to look through her stuff if she's around? Or, yeah, okay. So then, so that's what's happening with the experimental data for determining rate orders. Sorry guys, I got lost. So then here's your rate law summary. I think that this slide is actually really useful for studying. This gives you your rate laws and your integrated rate laws, and how then they relate to the plotting of the rate laws. So how the plots kind of look different and what you're plotting versus Y versus X. Your X-axis is always time, and then your Y-axis will change based on whether or not it's 0 order, first order, or second order. And then the half-life really only has anything to do with first order. You can use it for the other ones, but nobody does, and it's not as useful. So you won't see that. But basically what I'm saying is that you don't need to worry about half-life except for first order for this exam. You don't have to worry about half-life for 0 order or for second. So this, we only care about this. So this slide is really useful. Then we talked about reaction mechanisms. Whoops. And things that are tricky here is just your elementary reactions are describing a distinct event, while your chemical equations are talking about the whole overall reaction. So you're proposing a sequence of elementary steps with molecularity that's usually 1 or 2. Termolecular elementary reaction steps are very, very difficult to do. You guys can think of that from an entropic perspective. If I have to get this molecule, and then another one to all collide in space at the same time with the right orientation to get to the right thing, you can imagine how difficult that would be. So usually it's just a molecularity of 1 or 2. You write these without the state symbols. You also show individual atoms or molecules taking part in the reaction, and then you don't use any stoichiometric coefficients. So if I really did have 3 molecules of O2 running into each other to form 2 molecules of O3, then I would show O2 plus O2 plus O2 goes to O3 plus O3 in order for that to work. So you're writing out individual molecules and not using stoichiometric coefficients. So then what we talked about is verifying a mechanism. So this is the hardest part for students. I think this is where most of your questions were. And this is just when we have all of that experimental data, we've derived what the rate law is based on the experimental data, and then how do we propose and defend a mechanism. So when you're defending a mechanism, you're basically saying, what is my slow step, or what step am I arguing is the slow step, and then how do I derive an algebraic rate law from that slow step, and then that has to match the experimental data. And so basically when you're deriving rate laws from elementary reactions, these elementary reaction steps, the exponents now are related to the number of reactants in the elementary reaction. So again, this is my example that I just used of O2 plus O2 plus O2, which is now A. And so in that case, my rate would be equal to the rate constant of A cubed. If I have two molecules reacting with one molecule, that's going to be A squared B, which would still be a third order rate. So then these are kind of what we talked about, first order, second order. A and B are A squared in terms of finding these. So these are pretty unlikely. These are more likely, but if you're proposing term molecular elementary steps, then you're going to have a third order rate law associated with that mechanistic step. So then there's two ways to kind of derive rate laws. So let me good notes. I think I meant good practice for derived rate laws. So so here's some things that I think might have been missed when we kind of talked about it. So rate constants are always given subscripts associated with the steps. So if I have step 1, I'm going to have K1 for the first step and then K negative 1 for the reverse step. If I'm talking about the rate constant associated with step 3, I'm going to have K3 for the forward of that step and K negative 3 for the reverse of that step. So each individual elementary reaction is going to have its own rate constant associated with that step. Fast elementary reaction steps are considered reversible. If it's a slow step, it's not considered reversible. And so if I have a slow step, let's say step 4 is slow, I'm only going to have a K4 in the forward direction. But if steps 1, 2, and 3 are all fast, I'm going to have K1, K negative 1, K2, K negative 2, and K3 and K negative 3. So then the derived rate expressions can only include reagents or products or catalysts that can be measured. So no intermediates are allowed in your derived like mechanism that you derived algebraically. So if you end up with an intermediate, you have to then use the steady state equilibrium or pre-equilibrium method to substitute it out with things that you can measure. So things that you can measure are reagents or products, and I say products because sometimes you can get inhibition where you form a product, but then that product is kind of like inverse order. We talked about negative orders. So you guys probably won't see that in this class, but that's product you can measure, reagent you can measure, catalyst you can measure, intermediates you cannot. So, and then catalysts can appear in the derived rate laws. So then the difference between steady state equilibrium and pre-equilibrium is that steady state equilibrium, the main difference is that students don't like it because it's longer, but the more scientific explanation is that all intermediates formed and consumed will be at low enough concentration and have equal rates of consumption and formation, and therefore you can find all of the places, all of the steps where it's formed and subtract all of the places where it's consumed and set that equal to 0 and then solve for that intermediate and then plug it back into your derived rate expression. So that's the steady state equilibrium. Pre-equilibrium is a specific condition that either has to be told to you or that you are assuming, and that's where the forward and reverse rates of a fast step are equal, and so you can make the forward and reverse rates of that step equal and then solve for that intermediate and plug it in. Finally, the rate determining step is the slowest step that's going to govern the rate of all other steps, and then steps that follow the rate determining step are not used in the overall rate law. Basically, the rate determining step is the bottleneck of the reaction, and once everything gets over that high activation energy, the other steps don't actually matter. So that's kind of nice. Okay. So then we talked a little bit about rates and equilibrium, just the fact that your rate, I see a hand.
Hey, yeah, I had a
Zach.
question, Dr. Stowers. Okay, so going back to one of the last things you said on the last slide with the rate determining step.
Yep.
And so there's one or two mechanisms on sapling where, so you had a fast equilibrium step, and then you had a slow rate determining step, and then you had some other fast step afterwards.
Yep.
And so then the overall rate law included something that was produced in the rate determining step, but then consumed in the falling fast step.
Okay.
So that's what it threw me off, because to me, I would count that as an indeterminate, and you couldn't conclude that. Like you couldn't include it into the overall rate law. But
Yeah.
then there's also what you have at the bottom where it says like you neglect it, which that would make sense. I just like, if it's in the rate law, you can't really, I don't know. I don't know if that makes any sense.
Yeah, so the other thing that I think is key to figuring out your mechanism is to take all your steps and then add all your reagents and all of your products and cancel everything out and determine whether or not it's actually an intermediate or not. So you'd have to tell me the specific problem on sapling another time, and we'd have to look at it to see like what exactly you're saying. Because I'm the exact problem that you're talking about doesn't come to mind. But in terms of the best practices and the true things is that no rate expression should include an intermediate, even if it is that rate determining step.
Okay.
And that is true. So that's a thing. So yeah, so let me know. Let's follow up on that, and then if it's something that lots of people are confused about, we'll send out an email. So I'll talk to you about that problem later. But that's a good question, and it would be confusing if you're like, there's an exception. There's usually not exceptions. You're just going to write your rate expressions, including things that can be measured. Pretty much always.
All right,
okay.
Thanks.
Yeah, no, thanks. Good question. So then let's talk about rates and equilibrium. So, so your forward and reverse rates have these rate constants associated with them. And so they also have, if you set these rates equal to each other and then put all the reagents and products on one side and the rate constants on the other, what you end up deriving is that the ratio of the rate constants is equal to the equilibrium value. And so this is nice because if you have something where it favors the products, what that means is that the rate of the forward reaction is faster than the rate of the reverse reaction, etc. So, so that seems pretty straightforward, but it's a nice derivation that I'm sure somebody got a Nobel Prize for. And so then the Arrhenius equation is another way to look at the rate constants associated with temperature, and this is the modeling of the activation energy and molecules coming together and how temperature affects kind of this minimum energy needed for things to react. And so this is the equation, natural log of K equals natural log of A minus activation energy divided by RT. You can also derive an expression where you relate two different rate expressions at two different rate constants at two different temperatures, and that gives you this equation here. And so then A is the pre-exponential factor, which has a bunch of things in it, basically telling you that you need a certain concentration of A and B at a certain velocity, at a certain cross-sectional area, and in a specific orientation in order for things to work. So it's kind of amazing that reactions even happen. And so then activation energy relationship to rate constant and equilibrium. This is just saying that in endothermic reactions, the activation energy is going to be sensitive to heat, and if it's exothermic, it's not necessarily sensitive to heat. Okay, all right, 2 slides. So transition state theory is being able to draw out these reaction coordinate diagrams. So the x-axis is the progress of the reaction. The y-axis is the potential energy. Your activation energy is the energy difference between your reactant's energy starting point and the top of your slowest step. So this is a really easy reaction coordinate diagram because I only have 1 step. But if I had multiple steps, I would find my highest step, and then that would be my activation energy needed for my rate determining step. So the other thing that happens is that there's this activated complex that forms at the top of the reaction coordinate diagram, and this is where I have bonds being broken and formed kind of at the same time. And so then the catalyst is gonna increase the rate without being consumed, so it lowers the activation energy by allowing more reactant molecules to overcome the barrier. So basically it's forming a different pathway. It's not necessarily just saying, hey, come the same way, I'm going to lower the activation energy barrier. It creates a different path where they go through. And so catalysts, can appear in the rate law, but not in the balanced reaction. And so this is an example we had on one of the slides. finally, the only reason we talked about Michaelis-Menten is that it's a huge part of biochemistry that you guys will start seeing once you get into those classes. And sometimes when we derive rate laws, what we see is limiting cases where at low concentration it's like first order and at high concentration it's zero order. And that's what you see in Michaelis-Menten cases, is that in low concentrations of substrate, the rate's going to increase at a first order sort of situation, and then at high concentrations the rate will only increase with increases in enzyme. And so this is what ends up happening with Michaelis-Menten kinetics. Okay, so let's do questions. Hold on. Do we need to know all the different parts of A? So the pre-activation, I mean the, what's it called? What is that called? A. Pre-exponential factor A. So do you need to know all the different parts of the pre-exponential factor A? I think it would be good to know what factors are considered when thinking about whether or not a molecule will react. And so that's kind of like, it needs to have a certain velocity, speed associated with, to get to the right energy to react. And then you also need like that cross section, and then the kind of orientation as well. So that's, I guess you need to know all the different parts, but do you need to know how to derive it? No. Yep, Jack answered a question about activation energy. What other questions do you guys have? What's a part that feels sticky? And we'll go until 11 just in case you guys have more questions. And if you don't, we'll stop it at 10 minutes. So any slide you need me to talk through again? How's everyone doing? Lots of you are here. You're doing great. Thanks, Derek. I'm glad you're doing great. Are other people doing great? Does anybody have a question? Oh,
Schulier, yeah.
Yeah, Skylar said, can we derive a rate law? I get confused with the intermediates. Yeah, so let's, where is a rate law? I don't want to mess anything up. So let's do this. Let's do this rate law. So, so this is the overall reaction here. And this is your step 1, step 2, right? So, so in deriving this rate law, let's do case 1. Step 1, oops, is slow. So if that's the case, then what that means is that the rate is going to be equal to K1 times the concentration of CS2 times the concentration of N3 minus. And so N3 minus shows up here as a reactant. CS2 shows up here as a catalyst. And so those are both things that I can measure, right? So let's do case 2, step 2 is slow. So in that case, my rate is going to be equal to K2, concentration of S2CN3 minus, and the concentration of I3 minus. Oops. I3 minus. The other thing that's true is there's that 2, that stoichiometric coefficient 2 in front of the S2CN3. You see that? And so that means that this actually has to be squared, because elementary rate laws indicate that whatever your like 2 is, and again, this is an example where they did the thing that I told you not to do. So this should really look like this plus this plus this goes to this plus. So this is like, and then 3 molecules of these. So like, this is kind of starting to be ridiculous because we've got 3 molecules going to 1, 2, 3, 4, 5, 6, 7 molecules. So immediately you're like, oh, that's a terrible problem, but we're gonna keep going. Okay, so this one I didn't have to do anything to because everything in my initial rate expression in case 1, where this is the slow step, is all observable catalysts or observable reagents. In this example, though, I have a problem because this is an intermediate, and I know it's an intermediate because it's produced in step 1, it's reacted in step 2, and it doesn't show up in my overall reaction step. So that's how I'm defining it as an intermediate. Whereas the CS2 shows up in the first step and shows up in the last step, and shows up over the arrow. So that's a catalyst. Okay, so here's step 2. It's slow. What I'm now gonna assume is I'm gonna assume that step 1 is under pre-equilibrium. So if I assume that step 1 is under pre-equilibrium, that means that the forward reaction, K1 times CS2 times N3 minus is equal to K negative 1. Oops, this got capitalized. It's not supposed to be capitalized. K negative 1 times the concentration of S2 CN3 minus, right? So, so that is my pre-equilibrium equation. So now what I'm going to do is I'm going to solve for the intermediate using this equation. The forward and reverse reaction rates are the same. Are there problems you have to solve with steady state approximation? Yeah, so hold on to that question for a minute, Emily. So we're going to solve for intermediate. And so this copy equals this, whoops, divided by K negative 1. So far, hopefully we're following. And so now this intermediate is expressed in terms of the catalyst and in terms of the reagent. And so that can now be substituted back in to my rate expression, where I still have K2. And then I'm going to multiply by this, which is this value squared times I3 minus. And so that would be my, this would be my rate expression right here. This would be my rate. So this is my new K value, K2 times K1. K2 times K1 squared divided by K negative 1 squared is going to be equal to K. And then CS2 squared, N3 minus squared, and then I3 minus. So that would be my rate using the assumption of pre-equilibrium for this reaction. Does that help, Skylar and Kevin? Do you have a follow-up question for me before I answer Emily's question? No follow-ups? That helps a lot. Okay, good. Okay, so Emily's question is, are there problems you can solve with the steady state approximation, or can you solve every problem with pre-equilibrium? Yeah, so in like a world that is fun, we solve every problem with pre-equilibrium because it's so much easier. But that only happens if, that only happens in Chem 112 world. That only happens when we say, hey, solve this problem under pre-equilibrium. And it only happens in the real world when we have evidence to indicate that that first step is under pre-equilibrium. And so that isn't true. So there are problems you have to solve with steady state approximation because not every first step is under pre-equilibrium. So we're going to assume that no pre-equilibrium exists, and we have to use steady state approximation. So in that case, what I need to do is I need to find all the places. So what I need to do is I need to find my rate. Oh, it's capitalized for me. So I need to find my d dt of this intermediate. And I need to find all the places where it's formed and all the places where it's consumed, and then I need to set it equal to 0. So it is formed in the forward reaction of step 1. So that's going to be K1, CS2, N3 minus. So it's formed in that forward reaction, but then we're going to consume it in the reverse reaction. So K -1, S2CN3 minus. And then it is also, yes, so we're going to set it equal to 0 because according to steady state approximation, you're going to find all the forward and reverse rates, take your forward rates, take your rates of production minus your rates of consumption. We're assuming that that's at a constant concentration, so there's no change over time, and so we set that equal to 0. Okay, so we've got our forward, we've got our production, we've got our consumption in step 1, and now we need to use step 2. So step 2 is the S2CN3 being consumed, or is it being formed as I'm going forward in this step? And that is that it's being consumed, right? So I'm going to take minus K2 S2CN3 minus squared times I3 minus. Okay, so so I'm going to take this whole crazy thing right here. Sorry, I'm just trying to make it a little easier to see. And I'm going to set this equal to 0. And now what I'm going to do is I'm going to group terms, and this is actually going to be probably unsolvable in the next 3 minutes because we've got a squared term and a non-squared term. So what you've probably got to do is solve a quadratic. Yeah, you've got to solve a quadratic for this. Oops. Where, oops, hold on a second. So here's my, if I wrote this as a quadratic, what I would end up with is, this is my x, right here, and then this is x squared. Oops. So then here's x squared minus x plus the constant, and so then that's a, this is, so then a is K2 I3 minus, B is negative K to the -1, and C is K1 CS2 N3 minus. So then you could solve for X, which is the, S2 CN3 minus concentration, and then plug that back up into this rate expression, which is squared, which is nice because you're going to get like a square root of something. So that squared gives you then just that expression, and then that will give you your rate for steady state approximation, which again is really ugly. But that's what steady state approximation is. It's a little bit harder. So here's the parts where I went slow in my head, which are parts where you will mess up because we're all humans. This parts where I go slow is really keeping track of where it's being produced and where it's being consumed, and making sure I have my production minus my consumption. Or you can put all of your production on one side of an equal sign and all of your consumption on the other side of an equal sign, but that's where it gets tricky. And then the math is just kind of math. We're all good at math, but just kind of figuring out how to solve for the intermediate concentration. What assumptions do you make in the steady state approximation? You assume that the intermediate is being consumed and formed at the same rates, and that the concentration of that species is low. So those are the assumptions. 1, you're assuming that the consumption and the formation rates are equal, and 2, that the concentration of that intermediate is low. That's the assumptions that you're making. And so because of that, you then set your consumption equal to your formation, and then you solve for that intermediate. So hopefully that helped a little bit. Who asked this question? How do you steady state? That was Kevin. This is this was, what's the word? This was not satisfying because we didn't make it to the final answer. But does this clear up how to do it? Does that clear things up? No, yes? Yep. Okay. Okay. Other questions that you guys have? Perfect. I'm glad. I'm glad this is helping. Okay, if I don't have any questions right now, I'll answer Derek's question, which was kind of like, what's the format of exam 3? So exam 3, initially we had set up on Learning Suite where you would take a quiz before that kind of walked you through the exam, reminded you about honor code stuff, and then you could download the exam, take it at home, and then upload all of your pictures to Learning Suite. But right now we just heard from the people who know that Learning Suite is kind of backlogged and very buggy because it has so many users, more than it's ever had. And so as a result, we are under the assumption that Learning Suite is going to like crash on Monday as everyone's trying to upload their documents. So what we're probably going to end up doing is emailing you the exam and emailing you a Word document template for your answers. There is a time limit on the exam. The time limit is 3 hours and a half. Based on previous years, I can't remember what Dr. Paxton and I said. So from exam 3 last year, 95% of the class finished within 3.5 hours. So so we think that that's like a reasonable time limit to have for the exam. So we would email you guys, not from Learning Suite, have you write when you started the exam and where you ended the exam. And then we're actually going to provide you with a Word doc sheet that you can fill out in Word or in Tech or whatever, whatever word processing you use. And you would highlight the multiple choice answers and you would write in your answers in Word. And so this allows us to just get back a Word doc with your answers on it so that the TAs all have the same thing. It also doesn't require you guys to upload a picture or anything because you would just send back all of your work in Word. And so if you did have work, you would have to kind of like write it out like I've been doing, which again is not great, but at least we'll have all of your answers without kind of crashing the system. And that's kind of so that's the working plan as of today. And Dr. Paxton is working on revising it so that a lot more of the answers are kind of multiple choice or choose from options or kind of matching. So kind of what you've seen on Learning Suite, but not a Learning Suite interface, just an exam that's like you'll have it in front of you and you'll have the Word doc and then you can just kind of go through the Word doc and then send that back in. So that's the thing. Can we attach pictures of our work? So this, yeah. So that's the issue is the work. So I think it would be nice to be able to see your work, especially because we give so much partial credit with work. So what we might do is I'm going to have to talk to Dr. Paxton about what we want to do with work because I figured that you guys would want to do that. So maybe we'll allow like 1 page of work. So you kind of have to write small and kind of indicate where your work is so that you wouldn't have to have a lot of time formatting the work. Yeah. But the other thing we're doing is trying to not make it so that there is a bunch of work needed. You can kind of just answer the question. And then I think what we'll do is if you get the problem wrong, we'll like look at your work. But if you get it right, we'll just like assume your work is fine. I don't really know how this is going to go. This is totally new crazy world that I'm sad about because exams are easier when you can actually show your work. But so Kensley and Derek, we will allow some sort of way for you to have a picture of your work attached to the Word document. I think that is reasonable. We might have to limit like megabytes of data sending back, but that's a bridge I will talk to Dr. Paxton about later today. Okay, other questions on exam content? We're close to our hour here. And we're still recording. I forgot we were recording. Oh gosh, I've been probably doing super weird things. Okay. Any other questions? You guys doing okay? Okay. The other thing that's true is I know many of you are just kind of in survival mode at this point. So take a deep breath. this is not great conditions for anyone. Remember that at the end of the day, you can take a pass or a grade for the class. There's also like really good free apps associated with meditation, which sounds super weird to have that from a professor, but I think that at this point, if people could like take their mind off of something, that would be really useful. The other thing that's useful is exercising. So make sure you're kind of like getting that stir craziness out. And then as you prepare for exam 1, just make sure that you're reading through your notes and reading through the book and kind of going through what you need to be able to do your best on the exam. I will be available Friday at this time.